Hi, this is Jeff Heaton. Welcome to Applications of Deep Learning with Washington University. This is Module 9, Regularization and Dropout, Part 1, L1 and L2 regularization. Regularization is a very important technique for machine learning and neural networks in particular. Regularization is an attempt to basically reduce the complexity of a machine learning model, such as a neural network, by reducing the complexity of the weights in the neural network. This hopefully leads to a reduction in overfitting. Very complicated weighting structures often lead to overfitting because this is the neural network simply memorizing the input training and not allowing it to learn to abstract and to really generalize the problem so that it can make predictions on data that's outside of what it was trained upon. This module, we're going to look at several regularization types, and all of these are used to combat overfitting in the neural network in various ways. One even allows for feature selection, which is allowing certain inputs to be removed from the neural network if they're not particularly helpful. We'll start with L1 and L2 regularization. And then in a later part of this module, we'll look at a new and relatively simple regularization strategy for deep neural networks called dropout that is particularly effective. So when we talk about regularization, we're going to start with L1 and L2 regularization. You often see L1, L2 as parameters that you can set on a variety of machine learning algorithms. You don't just see this in neural networks. They originally came from linear regression sort of models. And for this module, we're going to first look at the linear regression form of this, completely separate of neural networks, and see what they look like, see what L1 and L2 are actually capable of. So here we have the helpful functions that we run each time. And this little function that we have right here is something that I'm providing that helps us to evaluate the coefficients of a simple linear model, such as linear regression. It would work for other coefficient-based models as well, like the various GLMs. So what this does is we give it the names of the inputs. So these are the x's. These are all of the values that the linear regression is building coefficients for. Then we provide an array that is the actual coefficients themselves. And there should be one coefficient for each input item and names. And then we also provide a way to report the intercept. In neural networks, this is the bias. In linear regression, this is the intercept. This is sort of the baseline of where everything starts from. So all the coefficients are multiplied by their respective inputs, their respective x's, and then added to the intercept. So the intercept is basically what happens if all of the inputs are 0. That would be the output. To do this, we create a data frame that has just 2 columns. It has the coefficient and then a Boolean indicating if the coefficient is positive or not. Greater than or equal to 0 is assumed to be positive. Then we sort by the coefficients. We display this nice sorted. So you're going to have the positive coefficients at the top, the negative coefficients at the bottom. It's not that the ones at the bottom are the least important. Actually, very negative coefficients are very important and very positive coefficients are very important. That area in the middle, that's the area that is not so important. And then we simply color it and display the plot. We'll see an example of this plot in just a moment. So we're going to start looking at how L1 and L2 are implemented in straight linear regression. This is using the miles per gallon data set. We're going to use the miles per gallon for both L1 and L2. So we're doing just straight old-fashioned linear regression. So the miles per gallon data set is the regression data set that we use to start with for most of our regression examples. Here I am not z-score encoding the various values. It's really not necessary for linear regression. That way we can see truly, if we did standardize those, it would just most likely decrease the size of the coefficients. But this really shows that big numbers like displacement will have a larger impact. You can also encode them. It can be done really either way. That's why I provide the code. You can uncomment it if you want to compare and contrast the results. And we encode the origin as a dummy variable. We convert it into x and y just like before, and we do split it into a train and test set. That way we can evaluate it on the test set. So to perform a linear regression, let's see, did I run that? I did not. So let's go ahead and run that. Okay, we've got our data loaded. So before we even get into L1 and L2, let's just run this as a standard regression problem. I am going to use scikit-learn. Now, TensorFlow does have the capability of doing linear regression all on its own, but we're just going to go ahead and use scikit-learn to keep things relatively simple. We're going to fit it. A lot of this looks very similar to how TensorFlow does things. Then we're going to fit, just like TensorFlow, and actually generate a prediction. This prediction, and again, just like TensorFlow, lets us calculate the root mean square error. And this code is all exactly like what we've done before. This area is a little bit different, though. Here we are converting the columns to a list, and we're removing miles per gallon. Miles per gallon, that's what we're trying to predict. So it does not have any sort of coefficient for it because it's what we're predicting. There's no input for it. And then we're going to report the coefficients with what we just created, where we're using the coefficient array in the linear regression. And we're also reporting the intercept to it. So let's go ahead and run this part. It trains very, very quickly. The root mean square is not that bad. This is a very simple data set, so neural networks really, honestly, are somewhat overkill for the miles per gallon data set, but it's a simple regression data set that allows us to very quickly train models and not have to spend a lot of time running the neural network. When we get to the Kaggle assignment, you'll get plenty of time to run long-running training sessions. But for now, we are simply using it. Here you can see the various coefficients and if they're positive or not. Positive means that they're positively correlated with the miles per gallon, with the target. Positively correlated means that large values in these tend to increase the target, whereas negative values means that the very negative values tend to decrease it. As far as importance, the least important ones are going to be near the middle here, because you can see in the bar chart that we have down here, these ones that are in the middle that are fairly flat, those are the least important. But these are very negatively correlated, and these are very positively correlated. If you want to just analyze these and interpret it, you can basically look at if origin was 1, you subtract that coefficient. If cylinders was, you multiply the cylinders by that and you add it. You multiply horsepower by that and you add it. All adding these to the intercept. And the intercept starts at -18. So if somehow you could get all these to 0, you would have a car that has a negative miles per gallon. I suppose it would produce gasoline as it went. Obviously, that's impossible. You can't have a zero-weight car anyway. And that's an important point in models such as neural networks and other ones. You don't want to pass in values that are outside of the expected range. Otherwise, it just doesn't make sense, like a zero-weight car or a negative-weight car. You want these values, you should check to make sure that they are truly in the range that the neural network was modeled on. And what these literally mean, I could set it up real quick in Excel and put in all these coefficients, and if you took the value here, filled them all in, multiplied each of these by the coefficient value, and then summed them and added the intercept, which is subtracting 18, you would get the approximation of what the miles per gallon is. It's literally an equation like that. So this shows you essentially the coefficient chart for linear regression without any regularization. This is just okay, and no, I do not want Windows to install right now. All right, so we will now continue with L1 regularization. So L1 regularization, we are going to modify the linear regression training algorithm so that it now adds a penalization factor onto it. Now the output, the prediction part of the linear regression is exactly the same. You cannot tell the difference between a linear regression that was trained with L1 or L2 versus another one. The output is all the same. You just add the coefficients together, like I said, and get your miles per gallon. The training is what's different. So L1 regularization, particularly when it applies to linear regression, is called Lasso. Lasso and Ridge, those are the two, L1 and L2. And by the way, for those of you in this class that are students, in machine learning and data science related jobs, questions about L1 and L2 are somewhat frequent for technical interviews when they're talking to you about data science. So it's good to be able to describe really how these actually work. So L1, the Lasso, is, I don't think you have to remember what the Lasso acronym stands for. I honestly never remember that. But what we are doing is we are calculating a sum of the absolute values of all of the weights. So for all of the weights that we have, we sum their absolute values. These weights can definitely go positive, negative. They can be through a whole wide range of things. So we sum up all the weights and we multiply them by a value called alpha, which is essentially, in machine learning algorithms, you have to tell it how big of an effect you want the L1 to have. Alpha is typically that coefficient. It's like a learning rate. It scales it. But you don't want to have really, really large values for that because these are being handled as an error. So the error from your neural network is basically how far off is the output from the expected output. The neural network training, the backpropagation algorithms that we're running and other algorithms, they try to shrink that error as much as possible. If you're adding the sum of the weights onto that error, it's going to try to shrink those weights too, because that's just an additive property of the weights. So it tries to shrink the weights down as well, We're taking the absolute values of that, because if we didn't take the absolute value and try to push all the weights to negative numbers, and that would really be bad. So we don't do that. And this is basically the L1 Lasso regularization. Let's go ahead and run it and see what it actually looks like. Linear regression tends to train very, very quickly. The root mean square error is a little bit worse than the previous one, but not by much. That's not always the case. Sometimes it will increase, but you now have multiple objectives. Your objective is not just to get that as low as possible. The goal is to keep the coefficients as low as possible too. And look at what this looks like compared to the other ones. It shrunk them quite a bit, but yet it's still getting the same output. So it's doing a lot more with a lot less of magnitude values on those coefficients. And notice several of these coefficients right in the middle, the least important ones, were pushed off to 0 altogether. They were essentially canceled out. That's called feature selection. You're picking which of these features are actually important to the neural network, or in this case, to the linear regression. So this forces it to potentially remove some of those. So the thing that you really want to remember, because that would be the good potential technical interview question, is which regularization technique can be used to feature select, to get rid of inputs that are not of value. And remember that that's L1, Lasso. I tend to almost just think of Lasso as like roping it and cutting them off altogether. That's just my memory trick for it. And the intercept is a little bit different. Oh yeah, and let me show you what that part down there is for. So the important parameter that we passed in, the alpha, is 0.1. So putting in a value for alpha is essentially that coefficient. That's showing how big of a weight you want to put on the weights themselves. How important is it to shrink the weights versus the rest of the inputs. So putting a bigger value in here will really defeat the ability. Like if we literally do 1.0 and you run it, you see it is really, really trying its best, and it's still getting a decent RMSE. But it's really doing its best to just squash out all those coefficients to 0. And as you can see, it's just saying, okay, I give up. We're just going to use the year, essentially, and a little bit of these three to predict it. But usually you don't want to go quite that extreme. But you can certainly play around with it and try to see what gets you the best root mean square. And by the way, one other thing about linear regression, the training is deterministic. So no matter how many times you run this, you run this, it ends in 184, still ends in 184. Which is not the same with neural networks. You tend to get a different value each time. So that gives you the, let's leave it at 0.1 I mean. This basically shows you sort of a calculation where I'm changing alpha. So 10 to the 0. This is with no alpha, so this would line up to linear regression. And as you increase it and as you decrease it, so this is this just shows you how you can, as you increase and as you decrease it, what it does to the actual error. Okay, the next one is L2 regularization or ridge regularization. You'll notice that it is, again, we're calculating the error. I will make that an E2 just to make it clearer. Because you can do L1 and L2 both at the same time. You can add them both in, and we'll see there's a technique for that. In TensorFlow, you're allowed to specify both of them. So here we're calculating just like before, except instead of taking the absolute value, we are squaring them. That has the same sort of effect of an absolute value-esque calculation, but so you don't have to worry about it trying to push all the weights down to negative numbers because it wants to minimize them. But it's a softer sort of graph, as we'll see the graphs of these two together in the next part. But it doesn't have that effect like Lasso has of completely turning off these coefficients altogether. So this is L2, or ridge regularization. I will go ahead and run it. It gets a little bit better of a final score than the previous one did. And you'll see, though, the coefficients are really pretty close to the original linear regression with nothing on there at all. And I was much more aggressive with the alpha in this case because it doesn't have a whole lot of effect on this particular data set. But this is how you do that. Now there is also something called ElastiNet. This really has nothing to do with deep learning. I do like to use ElastiNet, though, sometimes to ensemble deep neural networks together, and we'll see about that in a later module. Very common technique in Kaggle. But here we can run it. And this is ElastiNet, where it's basically, it's doing both of them. You can see that maybe some of the middle ones it pushed down on somewhat more than the others. They do look different, but this is telling it to try to really optimize both the L1 and the L2 sides. So this was just an introduction into L1 and L2, the roots from linear regression where they were created, and they can also be applied to TensorFlow, and we're going to see how to do that in the next part.